Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Before we jump into today's episode, a big thanks to everyone who listened to, shared, and commented on our AI Platform series. As always, we love hearing your feedback, and we've received a ton of it on these shows. Stay tuned for part 2 of the series early next year, and if you haven't yet, be sure to sign up for my upcoming series of ebooks on the topic, which we'll be releasing soon. Finally, over the next few weeks, I'll be bringing you great interviews from the AWS reInvent conference, which I'm at right now, NeurIPS, and KubeCon. And I'd love to connect with any listeners in attendance. So please shoot me a message via @SamCharrington on Twitter, email, or the TWIMLAI.com website if you'll be around. Today we're joined by Stuart Reid, Chief Scientist at Numerical Research. Numerical, based in Stellenbosch, South Africa, is an investment management firm that uses machine learning algorithms to make adaptive, unbiased, scalable, and testable trading decisions for its funds. In our conversation, Stuart and I dig into the way Numerical uses machine learning and deep learning models to support the firm's investment decisions. In particular, we focus on techniques for modeling non-stationary time series, of which financial markets are just one example. We start from first principles and look at stationary versus non-stationary time series, discuss some of the challenges of building models using financial data, explore issues like model interpretability, and much more. This was a very insightful conversation, which I expect will be useful not just for those in the fintech space. Enjoy. All right, everyone, I am on the line with Stuart Reid. Stuart is the Chief Scientist at Numerical Research. Stuart, welcome to This Week in Machine Learning and AI.
Yeah, thanks for having me, Sam. It's really great to be speaking to you. I've been listening to the podcast for a long time now, so it's great.
And I'm really glad we were able to connect. This one has taken a while to put together for a variety of reasons. We initially connected around the time, kind of in the run-up to the Deep Learning Indaba, which you participated in, and for whatever reason, it's taken us a bit to connect, but welcome once again.
Yeah, thank you very much. It was a pretty busy week during the Deep Learning Indaba, so I'm not surprised that it took a while, but good to finally be speaking to you.
So why don't we get started with a little bit of your background? You are currently focused on applying AI to finance. How did you get here?
Yeah, so I think that my interest in technology itself predates my interest in finance. I was actually the youngest South African to get an amateur radio license when I was 11. Oh, wow. And that's kind of when I got into technology. But soon afterwards, I discovered finance. Started out with the traditional books by, Warren Buffett and Benjamin Graham on security analysis and how do you actually value companies. And then that slowly shifted into some of the more modern approaches taken by like Renaissance Technologies and D.E. Shaw and AQR. And that's really quantitative finance. So that interest is actually what propelled me to study computer science in the first place.
And you're now, again, Chief Scientist at Numerical Research. What does Numerical Research do?
Yeah, so Numerical Research is a startup financial services provider based in Stellenbosch, South Africa. We have 2 investment funds, which are run entirely by machine learning algorithms. So that's what we do. We're using deep learning algorithms for the most part to predict what is going to happen in global financial markets, which sounds like the best idea ever, but it's incredibly challenging for a number of different reasons.
And we will get into those. The kind of way you framed your presentation, as I understand it, at the Indaba was around the application of machine learning to kind of the broader class of problems that you see in financial markets. And that is a specific type of time series analysis. And you made a distinction when we were talking before we got started between stationary versus non-stationary time series. Can you elaborate on that?
Yeah. So, a stationary time series is really one which is sampled from a distribution which doesn't change. So that fits quite nicely with your traditional machine learning paradigm, which is where you are fundamentally assuming that your data generating process is constant or very slowly time varying. But financial markets are anything but stationary. They're continuously changing. In fact, I would go as far as to say that the markets themselves are adversarial. They don't really want you to succeed. And this gets into the whole debate of like market efficiency. So my focus is very much on how can we get deep learning algorithms which were designed to work in a stationary environment under some reasonably strict assumptions. How can we get those algorithms to now work in an environment where you can not only experience a lot of non-stationary, but experience extreme shifts in the distribution of the data that is being generated? So these kind of points are regime shifts, structural breaks, critical transitions, change points. There's many names for them in the literature, but I prefer change points.
And so what are the main challenges that you see in doing this? Are there, is it just hard, or are there distinct challenges that you can point to in trying to apply machine learning and deep learning to these types of time series?
Okay. There are some very specific challenges. But let me first take a step back and say that if you are interested in applying deep learning algorithms to financial markets, there are more problems than just non-stationarity and kind of like this adversarial behavior. You also have a very challenging problem with signal to noise. So there's a lot of noise in financial markets. In fact, most derivatives that are priced these days are priced using random walk models. And that's kind of where my fascination with randomness comes in. But also markets are challenging because of this non-stationarity. But there are a number of different challenges associated with trying to predict time series which can abruptly change from one distribution to another one. And that's, can we actually detect these change points in a timely manner? And how many of these change points are actually going to occur? Is it a once-off kind of transition, as you might see in some ecological systems? Or is it a multi-way kind of transition, kind of like we have in finance, where you cycle between maybe a low volatility and a high volatility regime, or between a bear market and a bull market? Then the next challenge is the duration of that change point. So you can have change points which are extremely abrupt. Like, for example, if we're using change point analysis or machine learning algorithms to identify the onset of an attack on a network, like network intrusion detection, that's a very instantaneous kind of change in the distribution in that network activity. Whereas in financial markets, it's actually generally a slightly slower transition. And that can actually make it harder to detect because it's lots of small changes which kind of add up and eventually become a very large regime shift. Also, another challenge is the extensiveness of the regime shift. Is this regime shift, or is this change point affecting the entire model which we've trained, or is it just affecting a subset of the model? Is it just affecting the part of the model which is looking at interest rates, or the part of the model which is looking at currencies? And then the other two challenges is the magnitude, so very large or very small shifts and where those shifts are happening, and then the certainty around this. So how confident are we that we've identified a real change in the distribution as opposed to just an outlier or an anomaly in the data? So those are kind of like the challenges that you're presented with when you're trying to use deep learning algorithms to predict time series which are non-stationary and can have these abrupt transitions.
And when you're faced with those very distinct challenges, do you attempt to kind of pick them off one by one, or do they kind of together lead you to a class of solutions to, this general problem that has good properties for some subset of the challenges?
That's a very good question. I have definitely taken a very non-linear approach to solving this set of problems. In fact, I've only realized that some of them are problems quite recently. And it's kind of like an ongoing area of research for me. But generally, what kind of spurred the interest was that we developed this framework at Numerical, and we were training all of these different models. And one of the early things I noticed is that the best models were generally the ones which got the financial crisis right, like in terms of their predictions. So that motivated me to take a look at those models and try and work out, what made them get it right. And I think for the most part, it was luck for those models. But then I got really interested in these kind of like change points, because the reality is that significant changes in the distribution of financial markets not only affects how you should make your investment decisions, which affects everybody's retirement savings and their ability to do things, but also policy changes, when we're talking about how the government should decide to set interest rates, or how it should behave in situations like trade wars, these kind of things. So my approach to it was very much from an applied perspective. It was like, this is an interesting problem. And then I tried a whole bunch of different things to try and solve that problem, and then slowly began to see that it was a very common problem, which actually arises in many different areas, not just finance and economics, but also in statistical quality control, in manufacturing, speech recognition, medical condition monitoring, disaster prediction, if we're talking about like earthquakes, network intrusion detection. There's a whole bunch of really interesting ideas. And then through looking at all of the different applications, kind of piece together the theory and what the challenges are when you're looking at these kinds of time series. And what's interesting is that different parts of the literature from different domains are focusing on different subproblems. Like duration of the change point is a much bigger issue in ecology, for example, than in network intrusion detection. So I hope that kind of answers the question. It's a very good question. I have no idea. I'm just kind of going at it and seeing what happens.
You mentioned that one of the ways or one of the hallmarks of a good model is the ability to predict the financial crisis, which kind of suggests to me that, the main thing you're doing to test here is kind of back testing against historical financial data. And, I guess I'm wondering is what exactly, when we say, a model or these models, like, what exactly are we talking about? Is it one model that predicts the price of, the S&P or some portfolio, or do you have models for individual securities, or are you modeling, some of the subcomponents that you mentioned, like interest rates and bond prices and things like that? Like, how granular are the models that you're developing?
Yeah, that's a great question. So I think backtesting is a little bit of a swear word in finance.
Oh, is it?
Yeah. And it's
what did I just walk into?
So no, not at all. I mean, most people call it backtesting. I'm not a huge fan of the term, because backtesting kind of implies that we have some model, it has some parameters, and what we do is we pick a whole bunch of different parameters. We run a simulation on historical data, and we see which one did the best. And then generally that's the one that we pick going forward. And that's a very, very bad way to actually go about finding a good investment process, because inevitably what you're going to do is you're going to curve fit. You're going to memorize the historical data, and you're going to pick very suboptimal parameters going into the future. Mm-hmm. So what we prefer to do is really like a walk forward simulation through time, which arises a whole bunch of additional challenges. One of the challenges that we have in finance, which doesn't exist in some areas, is this issue of survivorship bias. So for example, the S&P 500, as you mentioned today, like the constituents of that are not the same as the S&P 500 from 1980 or 1995. You actually have stocks coming in and coming out, and more recently you have a lot of stocks going out and fewer like staying in that S&P for a long period of time. So we have this kind of like non-stationarity, not only in the time series dimension, but also in the cross section. So like what stocks are we actually looking at any particular point in time? And we can't just pick the S&P 500 today and run a simulation on that, because then we've introduced a massive bias. None of the stocks in our simulation can fail, which is obviously not at all reality. In reality, you have Enrons, which completely fail, and WorldComs, which also completely fail. So the process that we've taken has been quite systematic. It's like, how can we construct data sets which are truly representative of what the market looked like at that point in time? And as far as what models we're using go, we started off quite simple. Then we very much focused on the recurrent models, recurrent deep neural networks. And lately, we've actually had a lot of success with convolutional neural networks for time series analysis, which also seems to be picking up in the literature. And generally, we're looking at multivariate time series prediction. And I think that that's interesting because there is this whole covariance matrix that you're trying to model. It's not just about if we can predict what the stock is going to do into the future, it's how this stock is going to influence, these other stocks in the universe and how they evolve through time together as a collective. So as far as the number of models go, we actually want to have many, many different models, and then we kind of stack them together to generate better and better predictions. I think in our funds at the moment, we've got about 2,000 neural networks in production. Which is a challenge in and of itself. The engineering challenge is distinctly different to the theoretical challenge of how do you actually get the model to work in the first place. Mm-hmm. And those are continuously generating a lot of information, not just predictions, but measures of their confidences in those predictions, measures of their errors in the predictions. So there's a lot going on.
And can you speak at all to the granularity of those individual models? Or those 2,000 models all targeting, trying to predict the performance of some basket of securities? Or I'm imagining you're modeling different kind of underlying fundamentals. Is that the case?
Yeah, so definitely looking at different things in different models, but also using different inputs into different models to generate those predictions. We're trying to come up with a very diverse set of predictions, which we can then ensemble over. As far as the granularity of the data itself goes, this is another challenge that you get in finance, which maybe you don't get in other spaces, is that you have some really, really important data, which only comes out quarterly. If we're talking about like unemployment numbers, or we're talking about GDP, and all of these things obviously have an impact on the markets because people are looking at them and they're using that to make investment decisions on like which countries they should be allocating capital to and which sectors in those countries they should be allocating to, and then which stocks. But then you have this very high frequency data as well. So you've got price data, which is continuously coming at you. You've got volatility data. And what you want is a model which can actually weigh all of these time series, which may be occurring at very different time scales together in an unbiased way. It's a very hard problem. I'm not sure that we've got a perfect solution to it yet, but we've tried a lot of different things. Mm-hmm. Ensembling is the most obvious approach, and it's something that's worked quite well for us.
Are you also incorporating in like natural language processing types of models, or trying to get at information that's embedded in unstructured text and documents as well, or social media, things like that?
Yeah, this is an interesting question because I'm actually a little bit of a sentiment skeptic. That's not to say that, the sentiments that are extracted are wrong, but just consider the statement, sales are down $40 million for the quarter. Now, that is clearly a negative sentiment, right? I mean, sales, they're down for the quarter. But the reality is that if the analysts had expected sales to be down 60 million, and then they were only down 14, the market would actually probably rally in that situation. So I think that the challenge with sentiment analysis is really that there is a lot of context which is very hard to capture. So we've spent quite a bit of time working on natural language processing and building these kind of like sentiment scores and including that in our models. And one of the other challenges with using deep neural networks in finance is obviously the problem of black box, right? Is that it's very hard to interpret the models. And you recently had Sarah on your show, and I really enjoyed the discussion that she had about interpretability, because some people in machine learning seem to think that interpretability is a non-issue, but having spoken to many investors and many people who are interested in using this technology, but from outside of machine learning and computer science, interpretability is a big problem. So even if we did include these sentiment scores, it's actually quite challenging to work out if the model is using that data and if it's using it in an optimal way. That's kind of like a segue into another like sub-conversation. I mean, the main technique we're using there is really ablation studies and sensitivity analysis. But to answer the question, yeah, we've looked at sentiment. I personally am a little bit of a skeptic, but that's maybe because I can't tell what my models are doing.
So the general approach that you're taking is one of ensembling lots of models. Some might argue that, what you're doing is kind of feature engineering, and with a sophisticated and deep enough neural network and enough of the right data, the network could figure all that stuff out on its own, and you should be looking at that. Have you looked at that approach, and like how do you respond to that kind of approach?
Criticism. I would say that person is wrong. That's how I would respond. Okay, so this is another interesting discussion. You are very good at asking questions. I'm very impressed. In the machine learning community, data is considered to be like unreasonably effective, right?
Mm-hmm.
It's like the more data you have, the better your model is going to be. But my experience in trying to use, deep learning in finance has been quite the opposite. And I think that the analogy that fits it best is really that the markets are kind of like a haystack, and there are a few needles in there which correspond to, signals which you can extract and actually profit from. And when I get more data, so I go wider, I'm looking at more time series from more locations and whatnot. Generally, what I'm doing is I'm just throwing more hay on top of that haystack. So one of the challenges that we have is that and we're looking at about 400,000 independent time series at this stage. If I had to take all 400,000 of those time series and throw it into one model, it would almost certainly fail. And the main reason why is because of two things. One is it's an incredibly wide data set, so you've got a lot of columns, right? But the other problem is that because this data is inherently non-stationary, and now we're getting back to kind of like my main focus area, a very small subset of that data, if we're looking at, a time horizon, is actually relevant for predicting what's going to happen next. So your data kind of gets wider and wider and wider, but it's not necessarily getting deeper because the market fundamentally changed 2 years ago, and including data from 2014 is not actually helping. It actually makes my models worse because it's learning from a regime which is no longer representative of the data which is being generated now in the process.
Mm-hmm.
So one of the reasons why ensembling is a good approach is because we can actually take that very wide data set and carve it up into different subsets and give it to smaller models and then kind of aggregate them and stack them in that way. It's very difficult to do feature engineering with a very, very big model when your data is more wide than it is deep. I guess that's kind of my answer to that question. But I accept the criticism. Maybe I just don't have enough data.
One of the things that you talked about in your Indaba presentation, and if you're making the slides available to anyone, they're really, really interesting, and I'd encourage folks to take a look at them, and we'd be happy to link to them or post them someplace.
Yeah, I will definitely do that. They're just hyper animated in PowerPoint, so I've just got to turn them into videos and then, but I will do that. Yeah.
Okay. So one of the things that you talked about in that deck was online learning, which makes sense as a way to address this non-stationary nature of the signals that you're looking at. Can you talk a little bit about the way that you use online learning and what some of the challenges and discoveries you've made there are?
Yeah. Okay. So there are a lot of like intuitions and what I'm working on with my supervisor. I've actually decided to try postgraduate studies once again, is to try and codify these ideas and publish some of them. But online learning is for anybody who's listening who's not familiar, is really when you have a machine learning model and it's trained on some data up to a current point in time. And then what we do is we walk forward through time and we're using that model and we're just updating it on the most recent data which has happened. So there are a number of unique challenges that you face when you're doing online learning, which is when you do kind of one pattern at a time, or incremental learning, which is when you have a model, you move forward n steps, and then you update on the most recent n patterns or n plus some window size. So incremental kind of batch learning. And that's that by the time you have moved from, let's say, 2002 to 2007, you might have actually forgotten a lot of the stuff that you knew in 2002. The model has actually forgotten a lot of information, which means that when it enters into a regime such as the 2008 financial crisis, it actually doesn't know how to deal with that. Online learning is on the other hand, a very good approach because we have these different regimes. And if I had to just continuously include all of the available data in kind of like an expanding data set fashion, then my model would actually struggle to distinguish between the different regimes unless I had some sort of indicator of what regime the data was being sampled from. That's one of the challenges. One of the other challenges which we were talking about in the office today actually is for example, regularization. And this is, I don't know if it's published in the literature, and I'm not sure if I'm 100% right in what I'm saying. But different parts of the information which we're training our models on matter at different points in time. So if we had to take a neural network and we had to train it on, let's say, 2000 time series, and the first 500 time series were not relevant from the period 2002 to 2004. Slowly but surely, the regularization term in that neural network would push those weights very close to zero, right? But let's say from the period from 2004 to 2006, those first 500 time series which weren't relevant in the past, now all of a sudden become relevant in the future. Then we have a challenge, which is that we've actually pushed all of these weights very, very close to zero. And now we actually want to grow those weights again, which is just something which the models seem to struggle with through time. And the other challenge is that maybe the last 1,500 time series are now not relevant from 2004 to 2006, and it pushes all of those weights down to zero. So a lot of the assumptions, a lot of the ideas that we can apply successfully at a particular point in time. So if we just had to train a model on a data set, deploy it into production, can cause problems when we're doing an online or incremental learning approach. One of them is regularization. So, that we tend to bias ourselves towards, dropout kind of approaches as opposed to L1 or L2 regularization. But there are a lot of small issues like that.
One of the topics that you mentioned early on, but we haven't really dived into yet, is the types of models that you're using. And that seems particularly relevant to this discussion. When we think of kind of time series and models with memory and some of the comments you're making about, models remembering and forgetting things, I tend to think of recurrent networks. But it sounds like you're shifting increasingly to using CNNs. Where does that memorization element come from in a CNN?
Yeah, so none of them are particularly good at remembering data which is very far in the past. So let's say we have our data and it goes from 2002 all the way through to 2008. and we're training on 2 years worth of data or 4 years worth of data at a time. By the time we reach 2008, we're only really updating our model on data from 2004. We've forgotten 2001, 2002. We've forgotten what a financial crisis looks like. And whether you're using a convolutional neural network or an LSTM or a GRU or just a feed-forward neural network, you're going to run into similar problems because that regime is no longer in the data that you're training on. So you will forget it. So one of the techniques that I'm busy developing with my supervisor is kind of this idea of storing historical versions of your models in some sort of like explicit memory bank. And then, like, let's say you find 2008 and you're like, oh, my model is struggling, and we can identify that as struggling by looking at, change point analysis, and we can say, all right, well, there's been a significant change in the data. Our historical data from 2007 and 2006 is no longer relevant. What do? Either we reinitialize the model completely at that point in time, and we just hope to hell that it learns. Or what we could do is we could actually go backwards in time, and we could say, well, is there a point in time historically, like from a long time ago, where we learned something, we learned a representation which is relevant for the regime that we're in now? I hope that makes sense.
No, it makes a lot of sense. And I've heard of folks doing similar things from kind of at a model management perspective. So you've got some model in production and you've got kind of a constant evaluation system, and it determines that the model's performance has degraded, as opposed to, just immediately triggering a retrain. What some folks have done at least is to look at the historical models that have been in production and kind of test the current regime against those models and see if, as opposed to just us moving into new territory, we've reverted into territory, for which we've previously had a model, and, kind of switch to that one.
Precisely. So that's exactly kind of the approach that I've been working on lately.
Although it sounds like in this case at somewhat a lower level, in a sense of at the granularity of kind of the weights of the model or model, subcomponents, as opposed to kind of fully rolled models in production or something like that.
Yeah, so we're talking about like the weights.
Right.
So what we would do is we would walk forward through time, and we would actually drop these weights onto some sort of explicit memory so that we can load them at a later date. Now, what I'm thinking, and I haven't built anything like this yet, but it's just like an idea that's in my head, is really about whether we can model the transitions between those, because you can kind of think of the states that we're dropping onto this memory as being really states in like some sort of like Markov process.
Mm-hmm.
And kind of like where I'm heading with my research is whether we can model the transitions between these states and actually use it for simulation as well. But that's just an idea.
Interesting. And so kind of going back to the application of convolutional networks in this case, so you're feeding the CNN, let's call it a frame. Is that frame kind of a single point in time across a single time series, or a single point of time across multiple time series, or a historical frame that contains some time segment across, one or more time series? Like what goes into the CNN?
Oh yeah. So we're generally using like dilated convolutional neural networks. So
which means what?
Ones which are preserving the temporal structure of the data. So we're never feeding in, historical or future data into a historical node. So it's always kind of like WaveNet. I don't know if you've seen the diagrams on Google's blog.
Mm-hmm.
But what's going in is really an image of where you've got your stocks on, on the columns, and you've got a number of days at the bottom. So we're feeding in kind of like a picture, which is a whole bunch of time series put together, column by the amount of time. Yeah, I hope that makes sense. So if it's like 500 stocks and we're looking at, 40 days worth of data, at a frequency of 1 data point per day, then it would be a 500 by 40 image, which is basically going into that convolutional neural network.
Mm-hmm. And so the difference between that kind of situation and something like an LSTM is that your memory, if you will, is kind of limited by this fixed window, as opposed to something that kind of sticks around to varying degrees indefinitely. Is that right? And what are the implications of that in the way you model?
Yeah, so that is definitely true. And I must say that I was surprised myself that the convolutional neural networks generally perform quite well. I wouldn't have expected that. But we don't find a huge difference in the performance between our best convolutional neural networks and our best LSTM neural networks, or between the best like GRUs. Generally, they're all performing quite well. What makes a much bigger difference than architecture choice is the choice of other hyperparameters, like how much regularization are we adding, what kind of dropout are we using, how many layers are we using? Because the challenge with the data that we're looking at is because it's non-stationary, we can't look at all of the historical data. We can only look at the historical data that is relevant, so sampled from the same regime that we're in. Which means that if we have a very, very over-parameterized network, like extremely large or extremely deep, and then we shift into a new regime and we don't have that much data, that model actually can't converge with the amount of data that we have. So what matters far more than the choice of architecture in our situation has really been the hyperparameters that we're choosing for those. I mean, I'm pretty sure I could tune an LSTM to beat our best convolutional neural network or vice versa. Mm-hmm. I'm not sure if that comes back to the free lunch theorem or
right.
what, but they generally work differently. And because they work differently, they can really come up with predictions which are hopefully uncorrelated. And then when combined in an ensemble or in another neural network downstream, actually generate better and better predictions.
So beyond no free lunch implications, would you say that it also has something to do with the fact that your regime durations are short enough to be kind of captured in your CNN window, as opposed to something that might have maybe a longer tail?
Yeah, perhaps it's hard to say. This gets back to the interpretability discussion. Maybe we should ask Sarah. I'm not sure. Yeah.
So we started down this path in talking about online learning, and one of the challenges that you raised in your slides was this issue of kind of weight transfer and the ability to kind of capture knowledge and project it forward to the next time step. How have you kind of dealt with that? Am I capturing that issue correctly? The weight transfer?
Yeah, so I think, when we're doing online learning, we don't want to continuously reset the model. So we don't want to reinitialize it from scratch at every point in time, especially if the model that we had at the previous point in time or the previous batch is actually relevant for where we are now in time. So in that situation, we would like to transfer the weights from the previous model to the next model, but that doesn't hold when we're talking about a change point. So let's say, something happens and there's a massive structural break in financial markets, right? So now the previous model we have has really learned a representation of a world which no longer exists. We've moved on from that. When we transfer our weights from the previous point in time to the next point in time, we have a few options, right? So the first option is something we spoke about earlier, which is really going backwards in time and trying to find some optimal weights which work, and then transferring those into the model. But another approach would simply be to reinitialize the weights completely, which is extremely detrimental in the situation where you had a false positive. So you made a prediction that there has been a change point, that you've shifted from one regime into the next, but you didn't. Now, all of a sudden, you've reinitialized your model. You've forgotten everything that you learned previously, and all for nothing. So one of the things that we've also been playing around with is kind of like partial reinitialization, which is this idea that we take our weights and we actually pass them through some sort of noising function. So we add a little bit of randomness to those weights at every single point in time to kind of keep them fresh, keep them alive, and also give the model the ability to remember some of what it's learned in the past, but not all of it. I like to call it kind of like optimal brain damage. I know that there is actually something in machine learning called optimal brain damage, and this is not it. But I just love the name. It's kind of cool. It's like basically you have a model, you hit it on the head, and you hope that it learns something a little bit better than what it knew in the past. All of these ideas are just different things that we've tried, because I think that, to understand where we're coming from is, we, deep learning is like the solution, right? So we took these models and we applied it, and we realized quite quickly that financial markets don't care how smart your model is. They don't care how, deep the maths is, or how, optimal they work on ImageNet or on speech recognition problems. The market is this adversarial, very complex system. It's got non-stationarity in the cross-section, in the time series. It experiences these change points, which can be partial, affecting part of the model, or full, affecting, the full model itself. And they occur at kind of like a regular frequency. You would be surprised at how often they occur. So all of the ideas that we've tried, and my whole talk at the Deep Learning Indaba was really just a presentation of a whole bunch of tricks that we've tried, and some of them have worked particularly well, and some of them have not worked at all. I try to focus on the tricks that have worked as opposed to the tricks that haven't. But yeah, that's really where all of this is coming from. And I think like going forward, I'd like to formalize, some of those ideas and publish them.
Yeah, well, one of those tricks that caught my eye was using reinforcement learning as a way to I guess control the way you ensemble these models, or control can you talk a little bit about that?
Yeah, sure. So as I mentioned before, what matters more than the choice of model is the choice of hyperparameters. So for example, if we're using early stopping, which, some people don't like, I'm quite a fan of it. And the main reason why is because I'm doing continuous learning through time. I'm not training my model once. I'm training it, maybe 3,000 times. There's a parameter there, which is the patience. So how many epochs are you willing to see without improvement before you just stop training? And there's other parameters like your learning rate. And both of these parameters, your patience and your learning rate, should probably change if you experience a different regime or if you enter into a different state. If you think that you've moved from, one regime into another regime, it might actually make sense to increase your learning rate because you want to push your weights to a place which matches the new regime quicker. Or maybe what you want to do is you want to train for longer because you want to give your model more of an opportunity to actually fit the new regime. I hope that makes sense. So you can kind of think of these as the actions that a reinforcement learning agent can take. Mm-hmm. So it can change these hyperparameters in the models as we walk forward through time, depending on the state which it observes. So we're really using it as kind of like a meta optimization framework around each one of the individual agents in this massive ensemble. And that's been something that's been quite fun and it works quite well. It's not nearly as sophisticated as some of the reinforcement learning that's coming out these days, but it's worked quite well.
Nice.
And that's also a cheaper approach than just creating a bigger and bigger ensemble, right? Because what you could argue is, well, why don't you just create more agents with higher and lower learning rates or different patiences? And just grow that ensemble and make it bigger and bigger. And the main reason why I would want to use reinforcement learning instead of just making this ensemble bigger and bigger is because I only have so many computers.
Right, it's expensive.
And I have this thing called a hard drive. It fills up very, very quickly when I'm training these models. I mean, we're producing about 200 gigs of data a week. Luckily, we can delete a lot of it the next week, and we can compress a lot of it. But it's a challenge to actually train massive ensembles like this.
One of the other interesting tricks that I came across in your slides relates to kind of the challenge of identifying fundamental patterns in time series data when you can have differences in frequency and magnitude, but kind of the same underlying shape. And it can be difficult for networks to figure that out. And I hadn't come across this notion of dynamic time warping before.
Yeah, it's a very traditional technique. I think it's been used since the 70s.
Okay.
And there was a paper which came out, I think, in 2017, actually proposing a loss function for neural networks, which incorporates the idea of dynamic time warping. But essentially, just to quickly explain the idea, is that if we have two time series which are exactly identical in the sense that they have the same waveform, and they just occur over different intervals. Like, let's say we're looking at audio, because it's mostly been used for speech recognition, and I say the word apple, and then I say it really slow, apple. The waveform of me saying apple is the same, but the duration over which it occurred is different. So it's a different time scale. And one of the challenges with that is that if I had to do a Euclidean distance between those two waveforms, I would say that those two things were very different, when in fact they're actually very similar. They're the same thing. They just were said in a different way. So the idea behind dynamic time warping is really that you drop the one time series onto the one axis of a matrix, and you drop the other time series onto the other axis of a matrix, and then you use a procedure to actually draw a connection between the top right-hand corner and the bottom left-hand corner. Now, I can't remember, for the life of me, the exact details of the procedure, but the idea is that it's a more optimal measure of similarity between different time series. And one of the things that we've been looking at for that is really in time series clustering. So this is this idea of, if we have a time series and we chunk it up into different subsequences, can we measure the similarity between those things and kind of group them together? And time series clustering is another approach to change point analysis. That's one of the tricks which has not been very successful. It's very computationally expensive. And so I think that some of the papers which have come out on how to incorporate that into a loss function is maybe a more interesting approach.
Have you implemented any of those papers? Is that what you're doing? Or are you doing it more procedurally, like you mentioned?
Yeah, now we're getting into like some of the more secret sauce kind of stuff that we haven't. But loss function engineering is important. I'll just leave it at that.
Okay. Interesting. Yeah, when I saw that in the slide, I envisioned something that you would do kind of as a, maybe even pre-processing or kind of windowing or something like that. But the idea of building this right into a loss function is kind of interesting.
Yeah, I mean, there are papers out there about it. I recommend people go and Google it. We implemented that a while ago, though. That was probably almost 18 months ago that we looked at that.
So we have touched on just a few of the tricks in this set of slides, and we're starting to run out of time. You also mention and discuss in the slides time series embeddings. Embeddings have become a very hot topic of late. Can you talk a little bit about how they apply to time series?
Yeah, that is a great question. I'm a huge fan of autoencoders, variational autoencoders, and also, your traditional kind of dimensionality reduction techniques, multi-dimensional scaling, PCA, ICA, FCA. All of these techniques are quite useful at taking time series which have a lot of redundancy. So there's a lot of correlation, and actually reducing it down into a lower dimensional space, which really captures the statistical properties that are relevant. So the reason why we do that is because there is a lot of correlation in financial markets. And I think that I don't want to get into the debate of causation and the best way to go about that, because I'm not sure. But I think that it's difficult for the models to really assign importance to the different inputs when all of them look very, very similar. So let's say you had stock A, B, C, and D, and we know for a fact that, through domain knowledge or whatever, that A is influencing D. But maybe A is also kind of influencing B, C as well. So maybe the model would look at the correlations and say, well, B is maybe the influencer of D, and it would apply, the weights in that way. It's a bad explanation, but it's very hard to tease out what is causation and what is correlation in the data, and financial market data is incredibly correlated. So what we've been using the time series embeddings for is really to reduce this highly correlated space down into another subspace which has nicer statistical properties to predict. And the nice thing about decoding or autoencoding is that you then have a network that if I had to generate a prediction from this latent representation, I can actually then get it back into the original space. So maybe I have like 2,000 time series, which are all very similar. Maybe the Russell 2000 at this point in time. They're all driven by similar market forces. If Trump decides to tweet about something, they're all going to move in similar ways. And what we can do is we can really squeeze that down into a latent representation, which really captures the salient features which are useful for prediction. But the other nice thing about those features is that they have good statistical properties, especially if we're talking about a variational autoencoder. And then what we do is we decode back into the original space after we've generated our predictions in the latent space. I hope that makes sense. You can do it much more cheaply using principal components and those kind of more linear techniques. But I'm just very partial towards autoencoders and variational autoencoders.
And so do you end up with essentially a time series of these, or a time series in this embedding space, or is the embedding somehow, are you using that more statically, if that question makes sense?
Yeah, so what you end up with is another time series, but just of much lower dimension.
Right.
And preferably of better statistical quality, which we can then generate our predictions in. But it's still a time series, and it kind of like preserves the temporal ordering, the ordering of the data. So there are a few architectures that you can use for that.
And then you would use these embeddings as inputs to your other neural networks, the way you might with other kinds of embeddings.
Yeah, precisely. And then it generates a prediction in that space, and then we can actually decode back into the original space, because there is no point in predicting, let's say, the first two principal components, or predicting, this 5-dimensional latent representation learned by an autoencoder, because I don't know how to make decisions off of that. So we need to be able to actually get it back into the original space. So that we can make decisions about that, because it's no good knowing, what's going to happen to the first principal component or to the first dimension in this latent representation. How does that help me make construct a portfolio that somebody can invest in? Mm-hmm. Yeah, but the main reason for doing that is really just that the statistical properties that you get out are better than the statistical properties you put in. You don't have as many issues with co-integration and correlation between the time series. It doesn't help with regime shifts, which is the main focus of my research, but it has helped in improving the accuracy of the models.
Very early on in our chat, you mentioned that one of the techniques you use to kind of optimize these models and kind of explore these tricks is ablation studies. Is that worth a quick comment before we wrap up?
I'm a huge fan of ablation studies, yeah. But I mean, basically the idea is that if you've architected your neural network in a particular way, you can actually switch off parts of that neural network and measure the deterioration in your model's performance in the same language as whatever loss function you specified. And that's particularly useful when we go to investors or somebody who would like to understand or have some confidence in the models that we're using. We can say, well, listen, we can't tell you exactly what the functional form or the exact decision boundaries look like. But what we can tell you is that, these are the inputs which are contributing most to our model at this point in time. And I stress that at this point in time because the Ablation Studies, again, are applied in this kind of like online learning setting. And what's really interesting for me is just how much they change. I mean, you have at certain points in time, some variables are just absolutely, if you took it out of your model would be useless. But then fast forward a year or two into the future, I mean, that variable is it might as well be white noise going into the model, and some other variable is now driving, the performance of the model. So what's really interesting to me is really the dynamics of the neural networks, what inputs are mattering at what point in time, and then what I'm particularly interested in, and something I haven't spent a lot of time on, unfortunately, is then seeing how those kind of measures of variable importance match up to things like your business cycle. If we're at the end of a bull run, do we see that certain variables which we would expect to mattering more, and really seeing whether or not we can actually test economic theory using neural networks, and go beyond just fitting a function, but actually trying to understand what that function does. I hope that makes some sense, but I'm a huge fan of that particular approach, and I think anybody who's interested in interpretability should check out some of your previous podcasts. But that's the approach that we've found the easiest to implement and the most useful from an insights perspective. We're not necessarily using that for any decision making or to improve the model, but simply to understand what is going on in that model.
Awesome. Well, Stuart, any words of advice or pointers or kind of recommended resources for folks that are interested in the application of machine learning and deep learning to these types of time series, whether in finance or any of the other domains that you rattled off earlier?
Yeah, I think that there are a lot of really, really cool applications in time series analysis. And I think that there are very strong statistical motivations to spend some time looking at change point analysis and regime shifts, but also many applied motivations. So I'd recommend students who are listening to this to really, pick up the cause and do some research in it. But as far as advice goes, I'd say, expect to be unexpected, or expect to be surprised. Because financial markets, like I mentioned earlier, are almost adversarial in the way that they behave. And many of the things which we believe work in machine learning, I'm not sure that they do work. And you start to identify the cracks in the arguments when you apply these techniques to problems which they were not originally intended to be used for. I would just say you're going to be surprised at what you see, and also always be prudent. Don't train a model and then see that it's getting 75% accuracies predicting the S&P 500 and take all of your money and put it into that model, because I guarantee you it is wrong with that level of accuracy. If you're getting anything above 55% accuracy, you probably have a bug. That's just the reality of the game.
Awesome.
Yeah.
Well, Stuart, thank you.
It's a sombering end to every conversation. I'm very sorry to not being like, yeah, it's great. You should go and apply machine learning to finance. It's hard.
But it may save a listener a ton of money.
All right. I'll be very happy if that is the case.
Awesome.
Yeah. Invest in people who do this full time. That's what I'm suggesting.
Stuart, thanks so much for taking the time. It was a great chat.
Yeah, thank you very much, Sam. It was great to chat to you.
All right, everyone, that's our show for today. For more information on Stuart or any of the topics covered in this show, visit twimlai.com/talk/203. If you're a fan of the show and you haven't already done so, or you're a new listener and you like what you hear, please visit your Apple or Google podcast app and leave us a 5-star rating and review. Your reviews help inspire us to create more and better content, and they help new listeners find the show. As always, thanks so much for listening, and catch you next time.